All right. I see our main speakers here. Awesome. Let's get started. Thanks for showing up. Appreciate it. This is so awesome. All right, let me kick things off here. So thanks everyone for showing up tonight. And let me click the right window here. Someday I'll figure out soon. Welcome to the January meeting of the Central Florida Astronomical Society. My name is Frank Kane, your president, and you're in for a fun night tonight. But first of all, if you are not yet a member of the Central Florida Astronomical Society, you may be asking yourself, why should I join? Well, funny you should ask. I happen to have a list right here. You'll get access to our private events and dark sky viewing locations like the Geneva site, and we've got that coming up in a couple of weeks, hopefully, weather permitting. Access to our loaner telescope program, so we can loan you a scope for 3 months and you can get your hands on it and see what it's like. You have access to our online community through cfast.groups.io, where we have vibrant discussions about astronomy amongst ourselves. Quarterly meetings at the Seminole State Planetarium, which is the coolest venue for an astronomy club meeting. You also get membership into the Astronomical League as part of your membership, and that includes the Reflector magazine. And we are a nonprofit 501c3 organization, 100% volunteer powered. So we're just a bunch of people sharing our passion for the cosmos. And if you want to join up, head over to cfast.org, and you can do so there. Our agenda tonight, we're going to kick it right off with our main speaker, Dr. Michelle Thaller from NASA on the James Webb Space Telescope, followed by club news. So stick around for that. I got some announcements for y'all, so don't go away afterwards. And followed up by our Astrophotography Showcase, as always. Some quick housekeeping up front. If you do have questions, this is a normal Zoom meeting, so go ahead and use that chat box to submit any questions you have for Dr. Thaller, and we'll get to as many as we can when we're done. And with that, let me introduce our main speaker tonight. It is my great pleasure here to introduce from NASA's Goddard Space Flight Center. You may have seen her on the History Channel, the Science Channel, Discovery Plus, all over the place. Dr. Michelle Thaller, thanks so much for joining us tonight. Oh, I got you on mute.
I said, hey, thank you so much for having me. Yes, there I go. We just got a chance. I just got a chance to log in right now. So I think there might be an open mic.
I can't believe this.
Hey, anyone that's not muted, please mute.
That's no problem at all. I'm really looking forward to talking to all of you tonight, and I have some slides on the James Webb Space Telescope, and I'm willing to talk about any aspect of that. But I also am very willing to take this conversation any way you'd like to go. If there are things that you are very interested in hearing about, chances are I may have some slides on that. I may have heard about that. So if you'd like, I can start the presentation, and I'm happy to be taking questions as it goes. Would someone like to moderate the questions for me?
Yeah, I mean, we can keep an eye on the chat for any questions. And I mean, if anybody just wants to jump in, if you want to be like super interactive, you know, you can just do the raise hand thing in Zoom, I think. And,
it's totally up to you. So, you know, I guess I'll just sort of start right in. So to introduce myself, so my name is Michelle Thaller. I've been an astronomer at NASA for going on 27 years now. I started out at the Jet Propulsion Laboratory working on an infrared telescope called the Spitzer Space Telescope. And that was launched in 2003. And at the time, that was the largest infrared or heat-sensitive telescope that had ever been launched into space. And since then, I went to Goddard Space Flight Center, which is the largest of the NASA bases, in 2009. And I've been working on many different missions as a manager and a communication specialist. But the Webb telescope has been something of a focus for me. It's something that my husband worked on. It's something that was part of our family for years. So that's what I know a lot about. But I actually am asked to be a communication specialist for all of the missions at NASA. So if you have questions about anything else, that would be fine. So maybe the best thing to do would be for me to start to share my screen. Hold on a second. I will do that. Have I been made a presenter? Can I share my screen? Is everything good with that?
you should be able to. You are a co-host. Let me.
There we go.
Make sure.
I think that's what I need to do. There we go. Okay.
Cool.
And let me start my slides. Can you see a picture of a large NASA base looking thing, Goddard Space Flight Center?
Yes, we do.
Okay. This is actually only about, if I look at it, it's only about a quarter of the campus. So Goddard currently is NASA's largest base. We have about 10,000 people. And we specialize in the non-human spaceflight aspect of science. So, we're the center for things like the James Webb Space Telescope, the Hubble Space Telescope, which is now, I think 35 years old. We have involvement in the Mars rovers. We also do a tremendous amount in terms of space weather, whatever the sun is throwing out at us, and also all of the Earth science too. So at any given time, and this is what keeps me busy and also kind of sleepless at night, this is how many missions we have going on at Goddard. And you don't need to look at all of these acronyms, but this is sort of a chance for you to see. We are active in about 110 science missions. And this is actually a relatively small part of the NASA budget. It's actually, it turns out that in most years, the Pentagon spends more on air conditioning than it does on the NASA science budget. Seriously. So that's about that's about the budget you're looking at. And this sort of shows you all of the missions we're involved in, grouped into themes. The ones that are to do with the Earth are right around the Earth. And that is, I think, the biggest part of NASA science right now is all of the ways the Earth is changing, everything from the Landsat program, which is now close to 50 years old, to the latest Earth science satellites that are going up. This year in particular, we're launching a big satellite to monitor ocean health called PACE. And then you see we also have things around the sun. All of those missions you see around the sun are looking at what generates things like space weather, how the sun works, everything from the interior to how it generates the solar wind of particles. And you see some of our planetary missions around different planets, and then astrophysics are sort of up in a galaxy, so up on the left side. But there's such a range of science that we do. And so, I should be mostly conversant on these missions. It's hard for me to figure out exactly all of the discoveries that are coming in. That's sort of an embarrassment of riches. It's a nice problem to have. So tonight, we were going to talk a bit about the James Webb Space Telescope, and this is an artist conception of the James Webb Space Telescope out in space. I don't have many artist conceptions. I will let you know when I do. Most of these are actual images that I'll show. Of course, we actually did consider putting cameras on the telescope so you could see sort of what it was like out there. But one of the problems is that the telescope's operating temperature is minus 400 degrees Fahrenheit. And so they would have had to be made out of special materials, special things like that. So we in the end, we never put cameras out there. But here we have the James Webb Space Telescope. It's the largest and most complex observatory ever launched into space. The main mirror assembly that you see there, 18 segments. That's a little bit more than 20 feet across. And then you see this heat shield at the bottom, which is actually 5 layers of something called captain, which is very thin, almost mylar-like material. And the amazing thing to me is the journey we've been on. So the James Webb Space Telescope was officially approved for development in 1995. That was about the same time I entered service as an astronomer. And then it launched just a couple of years ago, and it's been a huge success. And I was actually just kind of scrambling before I came on because there was a new image that came out today that I really, really liked. And that's always something I like to try to do, is put something in that's very recent. So defining terms a little bit, I know a lot of you are familiar with multi-wavelength astronomy, but for those of you that might be a little bit new at this, the entire breadth of light that is available to observe the universe, we call the electromagnetic spectrum. And, visible light, as you see, there's sort of the little rainbow over here on the left-hand side, which represents the energies of light that our eyes are sensitive to. And the way we perceive the energies of light is color. Red light, for example, is a lower energy light than blue light. And so there's a very small range of light that our eyes are sensitive to. There's a huge amount of light that exists. And this spectrum doesn't really have an end. I mean, we've not detected the highest energy light yet because we don't have detectors that can do that. We haven't detected the lowest energy light because it's the same thing. So this is the range of light right now that we have the technology and the capability of detecting. And so the lowest energy light over on the right-hand side would be radio waves going through microwaves. And then you see this very large part of the spectrum that we define as infrared light. And infrared light, colloquially, we think of it as heat light. Right now, I'm emitting infrared light because that's the right temperature I'm at. In order to emit visible light, you have to be quite hot. You have to be glowing hot. So, for example, the surface of the sun is roughly 10,000 degrees. That emits visible light. And so the advantage about infrared light is that things that are lower temperature, like myself, or for example, like a planet around another star, these are things that if you have any sort of heat temperature at all, you will emit some visible light. And the amazing thing is that, when we say that infrared light is what we sort of think of as heat light, you can be far, far colder than a human being or a planet. As I mentioned, the operating temperature of the telescope is close to minus 400 degrees. So if you're anything above that, you show up in the telescope, which is pretty amazing. I mean, something that is minus 200 degrees Fahrenheit is warm by this definition. And then just on the other side of the spectrum, we've got ultraviolet and then X-rays and gamma rays. And those are produced by the hottest things in the universe, the most violent stuff. In order to naturally glow so hot that you're emitting an X-ray or a gamma ray, you need to be either millions of degrees or billions of degrees hot. And that's why it's so amazing to look at the universe in that kind of light, because you only see the most violent explosions, the hottest things in the universe, and everything else you just don't see when you look at gamma ray light. So the amazing thing about this whole spectrum is you see very different objects and very different views of the universe. And that's why we need to have telescopes that look at all of that. Somewhat fortunately for us, most of this light does not get through the atmosphere. Things like gamma rays and X-rays are stopped by the gases in our atmosphere. Ultraviolet, a little bit. Everyone knows you can get a sunburn, so we want to keep ultraviolet out. Infrared, most of the infrared spectrum does not get through the atmosphere. And water vapor is a very good absorber of infrared light. And the other thing, of course, is the gases in our atmosphere are warm. They're emitting infrared. So it's very hard to see that type of light. And so we really needed to get up into space to see it. And that was the motivation for building these different space telescopes. The Hubble Space Telescope sees a little bit into infrared, but mostly visible light. And then you have James Webb, and then Spitzer that I worked on as a postdoc at Caltech, sees even further into the infrared. So that's a little bit of a tour of the spectrum. So the Hubble Space Telescope is always larger than I think it is. I don't know if any of you have been to the Air and Space Museum and seen it. It's about the size of like a big boxcar on a train. It's a big thing. And this is an animation of what the James Webb Space Telescope looks like next to Hubble. The two observatories are very different design. And there are absolutely pros and cons to both of these. The Hubble Space Telescope over on the right has a very traditional design where you think of a telescope being a big tube, and at the bottom of that tube is a reflective mirror, and then that directs light into the instruments. And the protective tube is good for a number of reasons. It keeps stray light out, and also it means there's a very small amount of the telescope exposed to space. So if there are things like micrometeorites and space debris, a lot of that is actually hit, on the tube. And then the James Webb Space Telescope, the problem is that we knew we needed a really big mirror to do the job. The wavelength infrared is a longer wavelength. It's a lower energy light than visible light. And if you want to get the same resolution, if you want to get the same clarity of image, you need to have a bigger telescope to do that in this lower energy light. So the resolution, the resolving power, the clarity of the images of Hubble and Webb are very similar. They're about the same. Webb needed the bigger mirror because of that longer wavelength, low energy light to get that clarity. And of course, the bigger light bucket you have, the fainter objects you can see. So that's always really good too. So the problem with the Webb telescope, or say that the challenge, is that we just couldn't build a tube around a mirror that big. And so as you can see, the Webb mirror is just exposed to space. And yes, that means we do get hits from micrometeorites and space debris. We have on occasion had to refocus one of the segments, all 18 segments of that mirror. And once again, we wanted to launch a mirror big enough. We actually couldn't build one single mirror the way Hubble has inside it. We had to have a segmented mirror. And the mirror will actually fold up for launch, as you'll see. But the telescope is vulnerable to that. And so that's something that occasionally something's given us a good hit. We've had to refocus a mirror. Each one of the segments can actually tip and tilt very independently to form this really, really nice uniform mirror surface. The wonderful thing about it as well is that there's a fine focusing mechanism, which actually can actually change the curvature of the mirrors in steps of like 100 atoms at a time. Amazing. And so we actually do get a beautiful continuous surface from the 18 segments. So this is just a video. One thing that was amazing about working at Goddard was I got to spend my lunchtime looking in the window of this giant clean room. This is the largest, cleanest room that we know of on the planet. Here's a centrifuge where we exposed it to the amount of gravitational launch pressure it would need, the G-force. This is a giant shake table where we're shaking it to make sure that it'll withstand launch. If we're going to build something that's, $10 billion telescope, it better survive launch, right? I mean, otherwise it's a big piece of space debris. So, and this here is our acoustic chamber, where you see the whole configuration put in, where it's exposed to a level of sound that's actually fatal to humans. It would actually rattle apart the blood vessels in your brain. So this whole area of Goddard is like, 20 different fascinating ways to die. I mean, the G-force goes up to 30 Gs, which of course would kill anybody. Then we shipped it down to Houston. This is Chamber A, the largest, again, the largest vacuum chamber that we know of in the world. And this was actually used for the Apollo programs. They actually put whole Apollo capsules and astronauts in this chamber to test things out. And that was the only thing large enough to test just the mirror assembly. I mean, in this case, we're just testing the mirror. The instruments, the big sun shield, all had to be tested separately. And this is something at NASA that we're very familiar with. It also, of course, drives you insane, that we build things that are so big or so complex, you can't test it all at once. You have to test things one at a time and then hope they all work together well. And one of the more spectacular examples of this are like when we land on Mars, because we do that whole thing with the Mars landers where they come down on retro rockets. There is then a crane that lowers it down. And none of this can be rehearsed on Earth because all of those instruments were made to function in Mars gravity and Mars air pressure and Mars temperatures. So there's a lot of testing as well as we can do, and then hoping that the things work out. And of course, as I mentioned, the James Webb Space Telescope operates at extremely low temperatures. And so the mirrors were actually polished and shaped so that they're not the right shape at room temperature. And then as you take them down to cryospheric temperatures, then they snap into the right shape. So once again, really interesting testing about how this thing will work at low temperatures. The instruments as well are designed to be very, very efficient. I mean, I'm sure you know that, my light's a little harsh here. I'm going to move it over a little bit. I'm sure you know that time on these telescopes is incredibly sought after by astronomers around the world. And both Hubble and Webb are international public observatories. Anybody can write in. So if you have an idea about how to use the telescope, you actually can write in to NASA. There is a proposal time. And there are many committees of scientists that read and actually rate all of the different proposals that come to us. And so it's public. Anybody is allowed to observe it. And so time is very valuable. And one of the things that we do to make things very efficient is this array that you see here. And it looks like sort of 4 windows that have little dots and little bits missing from them. And that's deliberate. This is actually our micro shutter array on Webb. And to give you a sense about how big this is and how powerful this is, that array that you see, every one of those windows is about the size of a postage stamp, just a little bit bigger. And on each of those arrays, all those little dark spots that you saw on the one, if you look at all the little dark things, those are all individual little windows that open and shut electronically. They are microscopic. You need a microscope to see them all. And in a postage stamp, on each one of those arrays are 62,000 independent little shutters. Each one can be open and closed individually with an electric signal. So in total, with the size of about 4 posts, it's about this big, right? It's about that big. We have almost 250,000 little windows, 248,000 windows that can open up and close independently. And this is an actual microscope video of that. So what I might, so here are all those little windows. This is under a microscope so you can see them. And this is them opening and closing independently. And the idea is that we can look at many objects at once, both images and also taking spectra, taking different data. So if there are certain things we want to target on the sky that different people want to look at, we can actually take those observations in parallel. And so we can actually get things very quickly and then move on to what the next request is. And because of that, there's never been an observatory with the efficiency that this has. I mean, we can do, this is a data workhorse. I mean, it is pouring things out. And the amazing thing about, this big a telescope, looking at the wavelengths of light that it looks at, we've just never had an eye that sees like this. We've never had this powerful of a telescope look at these wavelengths before. So literally, I mean, you could close your eyes and point in a direction and tell Webb to look there, and you discover something new. That this is pure discovery space. And so, I mean, that's an amazing time of history to be in. This is just going out, and literally we've never had an eye that could see this way before. So everything you're going to see is going to be different than before. It's going to be new. In some cases, it's never have been seen before. So this is the large heat shield that actually makes it all work. In order to get this to work, if you're looking at infrared light, you need to be very cold. And we don't have any sort of cryogen, any sort of like liquid helium or liquid hydrogen. We don't have any coolant on board. We actually let the instruments come to temperature naturally. In one of our instruments, the mid-infrared instrument, there is a small electric cooler, almost like a little refrigerator. But other than that little, actually mechanical refrigerator, everything just comes to temperature being exposed to the cold part of space. That means that you can never get any light, any sunlight, any reflected light from the Earth or the moon. That would really damage the telescope. And so this is the heat shield. And this is a test that you see here of us very, very carefully unrolling the heat shield. And the heat shield has 5 different layers, and the vacuum of space between each of the layers protects the layer closer to the telescope. And so simply just letting this cool off in space, just passively, we'll take it to the temperature that we need. All right, and then here's a little bit more about that temperature. There's part of the heat shield that will always face the sun, always block out the sunlight. And I'll show you a diagram of our orbit and how this works in a little bit. But you've got 70 feet of sun shield, huge big sun shield, and that's always going to block the light out. And the warm side facing the sun gets pretty warm. The operating temperature is about 185 degrees Fahrenheit, right? I mean, not very comfortable for us. But that keeps the electronics working, and also it means that we get constant communication with the telescope. The telescope is always facing towards the inner part of the solar system, including Earth. And then facing away into space. Remember, in space, there's no air, so the temperature doesn't get moved around. If you're in shadow, you're cold. If you're in the sun, you're hot. And so the cold part gets down to close to 400 degrees below zero, so minus 388 degrees below zero. As well, those of you who love telescopes know there's a secondary mirror that usually comes out that focuses light into your instruments. The secondary mirror is on this huge boom arm. Here you see the telescope. We had to practice unfolding it, of course, many times. The side wings of the telescope are folded back to fit in the rocket. The whole thing just wouldn't fit in the largest lift vehicle we have right now, the Ariane 5. And here you see the almost origami nature of unfolding that heat shield. And there's the beautiful beast. The telescopes are coated with gold. Gold is very reflective in the infrared, and also doesn't tarnish, doesn't react chemically with anything around it. It's actually not very much gold because it's an electroplate of gold. It's only a couple hundred atoms thick. I think somebody said that in the entirety of this 20-foot telescope, there's about 5 wedding rings worth of gold. So it's actually not that much. But there's the whole thing being ready to launch. And you also see the secondary mirror assembly here folded up against the primary. And then it comes out during the deployment sequence. So this is just a little bit of I don't know whether there's a little bit of music. If you can't hear it, don't worry about it. But this is the main rocket, the Ariane 5. This is real video of moving up the Ariane 5 to where you can see the actual clean room on top, where we put the telescope into the fairing of the rocket in a clean setting, so there's no more contamination. The Ariane 5 is run by the European Space Agency. This was their major contribution. So, and there you see the telescope with the people around it, all folded up. This is real footage of them putting that telescope on top of the Ariane 5. Then we launched, and we were launching in December. We were right up against the rainy season in French Guiana. The European Space Agency has a launch site in South America. It was a pretty bad weather day. We were all hoping that would go off.
Engine start. And liftoff. Decollage liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
And here there is a camera on the rocket. There wasn't a camera on the telescope, but this is a camera on the rocket as we deploy. And that's the actual thing heading off now to 1 million miles away to its orbit. And the first thing that had to happen was it had to start making electricity on its own. And so you see that sun shield coming out. And as soon as we knew that came out, we knew we can turn it on now. And now it can make independent electricity. There we go.
The James Webb Space Telescope amidst applause here in the Mission Control Center, now taking its first steps in pursuit of cosmological discovery.
So it's worth mentioning that the launch was so perfect that it actually saved us years of lifetime on the telescope. Sometimes I get a little bit embarrassed when people say that, oh, NASA managed to send a spacecraft all the way to Pluto, and that's like hitting a hole in one, over 1,000 miles. And it's like, well, we do have rockets that help us guide. It doesn't have to be like just one single thing. And we can make some corrections. Now, I mean, we can't correct if it's terrible, if it gets us on totally the wrong orbit, but little corrections we can make. And the Ariane 5 simply put us on the perfect trajectory. We didn't even need to turn on the guidance engines. And so all that fuel was saved for the life of the telescope coming ahead. And so we hope that this telescope will be operating for decades. And that's something we have, something to look forward to. So it was an absolutely perfect launch. You guys already saw that, so I'm just going to go on. All right, now this is the thing that happened next, and it was a wonderful 2 months of my life. It also, I'm sure, took years off my actual lifespan, because the amount of stress in seeing if all of these things were going to work to unfold and to actually get this telescope. I will say this, I did not personally like the design. It seemed very complicated. And my husband was an engineer on the telescope, was a senior engineer on the telescope. And he would just be lying in bed at night going, oh, it's not going to work. It's not going to work. But the amazing thing, and I'll just let this video go. There were 344 single point failures on unfolding this thing, right? I mean, different little actuators had to release, pulleys had to pull, things had to not tear that they had in testing and all of that. And you can see here, 140 release mechanisms. There were motors that had to pull stuff back. The deployment motors, were cooling off naturally as we went farther and farther out into space. And while the motors did have heaters, they wouldn't work when it had finally cooled down to its operating temperature. So there was a time element to this. We had to get this stuff going and deploying immediately, because the warmer the stuff was, the better the deployment motors would work. And I mean, things would be less frozen up than when it started. So the day after launch, we started sending the signals with all of these things. And I was there. Some of them, at first, we didn't think were working, but then they did, and all of that. But 400 pulleys, 90 cables, 70 hinge assemblies, 344 single point failures, and they all worked. That was, like I said, that was an incredible couple of weeks, and it wasn't always smooth, but it was. I mean, it worked, and that was the amazing thing. So where was it headed? For an infrared telescope, a really good place is to get it outside of anything warm in the way. And so the Hubble Space Telescope, for example, actually orbits the Earth. So, I mean, once every 90 minutes, the Hubble goes around. And Webb, we had a different strategy. We wanted to send it way out into the solar system, beyond the Earth and the Moon, about 1 million miles away from us. And the reason there is, of course, now everything warm is all in one direction, and the heat shield can protect you for that. The moon, the Earth, the sun are all in one direction, and you can look out in space the other direction. And then, of course, over the whole year, you get to see the whole sky. So I mean, as this thing looks out over a whole year, now it sees the entire sky. Scheduling our first observations was frustrating and fun. because the launch date kept changing. And so that meant the direction you look out in the universe kept changing. So we had different sets of observations for our first observations, depending on what the launch date was, all these things you don't think about. So Webb is orbiting something we call L2, the second Lagrange point. And again, I think a lot of you are familiar with Lagrange points. If you're not, they are a place where there are balances of the forces in the universe, the solar system, I should say, and you can stick things in and allow gravity and for example, sort of centripetal force to kind of keep you in one place. The probably the easiest to understand Lagrange point is the first one, L1, which is the place between the sun and the earth, where if you were along this line, the gravity would be the same in both directions. Your attraction to the earth and the attraction to the sun would be the same. And of course, that would be much closer to the earth because the earth has a lot less mass than the sun. So think about balancing something, and that balance point is what we call a Lagrange point. And then L2 is a Lagrange point on the other side of the Earth. And that's a balance of all of the gravity of everything in the row, the moon, the Earth, the sun, that whole system in a row. And that's balanced sort of by the centripetal force of the orbit. The orbit is kind of throwing you out a little bit. And then the balance is tugging you in. And there's a place where you can stick a spacecraft. And it really doesn't take a lot of fuel to keep it there because all of the forces are balancing and naturally sticking it into space. So here's an animation of us. We orbit gently around this Lagrange point and always have the heat shield facing towards the sun and the earth and have the dark part of the telescope facing out. So that's how we observe with Webb. And then we can do some guiding within that range of being out, looking out away from the anything warm. So that's kind of the first part of the talk. I wanted to talk a bit about the engineering aspects of Webb, and now I'm going to go on to talk a bit about some of the science that we do. I don't know whether I might just check out the chat and see if there's any questions.
Yeah, we got a couple that have come in, so if you want to take a little break for that. David LeGros asks, how does the Webb adjust the focal length? Pictures of planets in almost infinity need adjustment. I think you talked about curving the mirror to do that, right?
Well, the mirror doesn't really curve to change focal length.
Okay.
So, in that case, I mean, we basically have the mirror set on infinity, the focus set on infinity. And I mean, even things that are in our own solar system are basically at infinity, compared to where the Webb is. So, the Webb is here at Earth, just a million miles away. And we have imaged things. We've taken beautiful images of Jupiter and Saturn, Uranus and Neptune. And so we didn't change the focus of the telescope. It's basically one focus, and that works for anything that's sort of so far away. I mean, if the telescope is a million miles away from Earth, but we're taking a picture of Jupiter, which is, oh, I should know offhand, but say I think it's like maybe 200 million miles away, something like that. I mean, it's a little more. You really just need the one focal length.
Gotcha.
And says, what other instruments? Oh, is there a calculated expected failure rate on the shutters? Probably somewhere. Yeah, I don't know. I mean, the nice thing about the shutters is that obviously we think some of them are going to fail and basically create what are bad pixels. So, I mean, as the telescope looks out into space, we don't have to use the micro shutters. We have other ways of getting the light into the telescope, but basically there'll be like a bad pixel, and then depending on how the telescope is oriented, you can just use different pixels. You can use just different shutters. It's not the kind of thing where if one shutter closes and won't open, we'll never see that part of the sky again. You're allowed. There's some variation in both rotating and aiming that you can just use a different micro shutter to get that particular thing that you're looking at. It says, what other instruments are using L2? There's a lot out at L2, actually. We use L2 for a lot of our instruments that observe the deep universe, the cosmic microwave background radiation things. Those were all out at L2. I'm trying to think what else is out. I mean, I'm sure you can Google, what spacecraft are at L2 right now. We've certainly used L2 before, both for NASA and for commercial stuff. And I'm pretty sure there's plenty of military stuff out there too, I would think. So yeah, it's a relatively crowded place, but we know the orbits of everything out there. I think that's all the ones for here right now. Okay.
Yeah, I think we saw the Euclid Space Telescope launch out there not too long ago here.
That's right, Euclid. Yeah, Euclid's out there too. Yeah. Yeah,
Very cool.
it's like I said, it's a great place to look out into the universe without using a lot of fuel. So it makes sense that we use that.
Very cool. I'm going to sneak in a question of my own if I can. So
Oh, sure.
you mentioned that the expected lifetime was hopefully decades. Why so long? I mean, is it like a lack of moving parts relative to Hubble, or what? Where does that longevity come from?
Well, it does have a limited amount of fuel to aim it and to guide it. And so I think that that will probably be the limiting part of the lifetime, and that was why the launch was so important to us, because the sort of the success, the success criterion of the mission was we wanted to be able to operate for 10 years. And things were similar with Hubble. I mean, with Hubble, we also wanted to operate 10 years. Now we've gone on like, 35. The difference is that Hubble has been able to be serviced by astronauts. And Webb is so far away, we don't have anything that can bring astronauts, at least now, out to service it. Whether that might be different in 20 years, who knows? But right now, there's no way to refill the fuel on it, the guidance fuel. So that will, that's the main limitation. We have, like I said, we've already gotten some pretty decent smacks from micrometeorites. That will also limit the life to some extent. Although, again, when you have just a little bit of a micrometeorite embedded in the mirror, the mirrors don't really crack. When something hits that mirror, it'll just kind of embed in the mirror. That doesn't do much harm to the telescope. It takes out a little bit of the light gathering capability, but not much. So I think, the guidance fuel is the main limitation. And there is less of that than we had at Hubble, and Hubble was able to be refueled a couple times too. And they replaced the gyros, and they made it, we replaced the cameras and all of that. In fact, the image you see in front of you, this is actually a picture from the Hubble Space Telescope, and this is from one of the new cameras, the advanced camera for surveys, which was put up in 2009. So, I mean, Hubble launching, a long time ago, but 2009 was the last time we were able to service it. We can't service it anymore. At the moment, it would use the space shuttle, and the space shuttle program ended, and so we don't have any way to get out to the Hubble. The Hubble's not in the same orbit as the space station. If you saw the movie Gravity with Sandra Bullock and all that, one of the things that was so amusing was that everything was basically in the same orbit. It's like, yeah, we can kick off and we'll get to the Chinese space station. Not so much. Yeah, and unfortunately, there's nothing right now that gets humans out to the Hubble. In the last mission, they did leave a grappling ring on the telescope. So if a robot can actually get out there and grapple, mainly that was thought of as safely deorbiting the telescope. When the telescope is finally non-operational, we'll send a little rocket pack up there that'll grapple on and take it safely down probably into the Pacific Ocean. There's actually an area of the Pacific Ocean that's a spacecraft graveyard. We deliberately put things down there so that they're away from anything. They can't hurt anybody. They're not going to hit anybody. And also that there's this salvage works from like the Navy and stuff to bring stuff back from there. So I mean, it'll probably go into that spaceship graveyard. Yeah.
Cool. Thanks.
Sure. So as I mentioned, this is a Hubble image. This is not a Webb image. And this is of one of the more famous objects that Hubble ever looked at. And I want to show you sort of why we use Webb, because we see very different views of this. So this is the famous Pillars of Creation. And it was one of the first images made by the refocused Hubble after we launched it with a mirror that was perfectly round to the wrong curvature. And it's a beautiful, beautiful image. And I'll show you a bit more about the context of this image. And one of the things that is astonishing about this is a nebula or a cloud of gas and dust in our galaxy. And the main sort of large finger here over on the left. So the finger that, if you can see my cursor, the top to the bottom of this sort of finger of gas is actually about 5 light years across from top to bottom. And a light year being about 6 trillion miles, you've got about 30 trillion miles there. And it amazes me that this, of course, the nearest star to us is about 4 light years away. And so if we were over here by the nebula, this huge cloud of dust would actually extend all the way out to the nearest star and beyond. So this is gigantic. And there are multiple stars forming inside this cloud right now. All you need is a denser part of the cloud. That's all you need. Let gravity do the rest. When part of the cloud becomes denser, it will start to attract things gravitationally more than the rest of the cloud. And when you've got 30 trillion miles of dust and gas to start drawing on. All of a sudden, you can get a lot of stuff cramming itself into the middle of this denser area. When that center reaches some tens of millions of degrees, just from all this stuff falling down on it, just that, it will ignite a natural nuclear fusion reaction. Hydrogen will start to smack into different hydrogen atoms and fuse into a helium atom. And that's just because there's so much pressure and heat. The gas is under incredible pressure, and it's so hot that the atoms are moving around so fast. And if you can get hydrogen atoms really close to each other, something called the strong nuclear force kicks in and they stick. And that's a nuclear fusion reaction. And so stars are the only sources that we know of right now where you naturally have nuclear fusion going on. That's what a star is. I mean, that's how we make the atoms of the universe. So I mean, it's wonderful to think that's what's going on. And to give you a little context about this, this is actually, let's see, there we go. This is actually a small part of a much larger star formation cloud complex called the Eagle Nebula. And you can see the famous pillars of creation here right in the middle. And the reason they are that shape is if you notice up here, there's a collection of very bright pink objects that are actually a group of massive stars that are more massive than the sun. And they are busy blowing a bubble in this cloud that they've just formed out of. So the stars ignited their nuclear fusion reactions, and a wind of particles and heat and radiation is coming off these young stars. And you can see there's even a shape that it's actually blowing sort of a round bubble. And then what's happening with the pillars of creation is that there are other stars forming here in dense regions at the top of these pillars, and they're holding on to the gas and the dust against this wind of particles from the new stars. So, I mean, the reason they're that weird sort of finger shaped is that they're almost like comets. They're being blown away by the wind from these new stars, but there are dense regions in there that are holding together against that wind. And you see these beautiful shapes that are blown by all these bubbles of these new stars. So going back to the Hubble picture, each pink dot that you see there is a star. We're talking light years and light years of space here. And now I'll switch to the infrared version that we see with Webb. So this is visible light with Hubble. And then with Webb, this is the infrared version. And, so just explaining what you see here. Of course, we don't see infrared. So what we do at NASA is we assign visible colors in an image like this to match different energies of infrared. And we try roughly to keep the spectrum, blue is higher energy, red is lower energy. We roughly try to keep that color scheme. If you want to, you can download exactly what energy of light we assign each color in an image like this. So yes, this is false color, but all of this is real data, real infrared data, just simply assigned to colors that we can see with our eyes. And what I love to do is look at the number of stars. So I mean, yeah, because that's how many stars we see in that visible image, and this is how many we see in the infrared. And it really highlights one of the advantages of infrared. All of these stars are there in our galaxy. Most of them are not even associated with the nebula. They're much, much farther away in the background. But we're not used to the fact that we live in a dust ring. The galaxy, the plane of the galaxy, the Milky Way, is chock full of debris and dust from exploded stars and all kinds of stuff. And that blocks out a lot of the light. We live in sort of this foggy, smoky space environment. And, here you see all that infrared light cutting right through that. And you get some wonderful views of the stars beyond. But then also, we're going to hone in on this. You can see what's going on with star formation right at the very tips of these pillars. And we're going to look at this one in particular. So this is another color, another energy of infrared. In this case, a slightly lower energy, which really brings out the dust itself. The dust, most of this dust in space, light years of dust, most of the dust is very cold. It really only gets hot where it's very close to a star that's forming inside. And so you can see all this beautiful cold dust. And then at the very tops of the pillars, you can see this reddish color is a lot of heat coming through the dust. And that's where we see active star formation going on right now. And another slightly different color spread, but this is beginning to look into that cloud and see this hot region where we have all of that gas and dust coming together to form a young star. And once again, look at all the stars here. I mean, this is amazing. Every one of these is real. Every one of these is a star we had not seen before, either in the foreground or in the nebula or beyond. It's just an entirely different view of the galaxy. So this is a different star-forming region. This is a region called Rho Ophiuchus. And this here, we can actually look closer down into the cloud itself to see where the stars are forming. And what we have in here, and I'll try to give you a little bit of a guide, is we have a party of star formation going on. So when stars first turn their nuclear reactions on, they're not very stable. I mean, a star is at its simplest an out of control nuclear bomb. It's just there's a fusion reaction. It just wants to explode. But there's so much material around it that the gravity, just the gravity of that material keeps it from exploding. It's an explosion that's too big to explode. There's so much stuff that gravity itself holds it in. It's exploding out with nuclear reactions, but there's all this gas, dust, everything else, and that holds it in just gravitationally. And so there's this wonderful balance between the explosion and gravity. And young stars don't really get that right at first. They're kind of, a little bit unstable, and they tend to send these jets of material off along their magnetic poles. So the sun has a north and south pole, just like the Earth does. And so some of this material gets jetted off along the poles. And so what you see here is a bunch of stars doing that. So this is one jet complex here. There's a jet, this red material. So there's a star forming probably right about in here. And then there's a big jet coming out in this direction and this direction. There's two big jets coming out in the background over here. So there's probably stars forming, right about here where we see this bright area. And then there's this big jets of material. And there's also really cute little ones. Like here's a young star here with two jets. It's a small one. They're all over the place. They're just, I mean, you can just see layer upon layer of these new stars inside Rho Ophiuchus. I mean, this is the ability to look inside the dust, right? You can't see this with visible light. This is all hidden inside the dust cloud itself. It's amazing to see it right in front of you. And this is another cloud where you can really see the jet in detail. The star that's forming is still in a cocoon of dark dust. It's blocking out the light, even the infrared light, so dense. But you see these giant jets, and they can be light years across. And you can see that the young star turning on inside the cloud. So it's really a ringside seat to actually watch these stars form. And when you can look at, millions of them, perhaps across the galaxy, you can really piece together how this process works. And so we're looking into a lot of that with Webb. Stars, of course, there's the other end of the life cycle, right? They're like us. They're born, the nuclear reactions go on for a while, but then they run out of nuclear fuel. And at first, what happens is that in the core, the hydrogen is converted into helium. Then you just have helium left over, and helium is harder to fuse because helium actually has, I mean, the reason atoms don't want to fuse together is because of the electric charge, right? So the nucleus of an atom has a positive charge. Hydrogen has a +1 positive charge. And so in order to get things to fuse, you got to get them close enough to overcome that electric repulsion of like charges don't want to get close to each other. Helium now has two protons, 2 times that electric charge. It really doesn't want to fuse at all. But if nothing is actually feeding that reaction, then what will happen is that star, we said gravity is basically pushing that star together. If the reactions are sputtering out inside the core, the gravity can kind of condense things more, rise the temperature even hotter, and fuse bigger atoms that are harder to fuse, like helium. And stars like the sun will kind of go through, they'll probably maybe get up to carbon. They'll probably be able to make atoms as big as carbon, but after that, there just will never be the pressure to actually get things close together, and the fusion reactions just die away. So our sun will die a relatively quiet death, just the reactions will kind of go out. But this is a wonderful Webb picture of a star that was once more massive than the sun. It exploded violently. And this is the Crab Nebula. So this is the infrared version of the Crab Nebula. The Crab Nebula is it's on the order of about let's see, it's right now I think it's about 10 light years across. It's still expanding outward at millions of miles an hour. So this thing is still exploding and evolving. We think that the star that created this exploded about 1,000 years ago. And you can actually see what's left over at the very heart of this. There's a little bright area right here. And that is actually the location of something called a neutron star, which I could talk to you all night about. They're one of my favorite things in space. And that's the collapsed core of this giant star. The explosion basically collapses the core and then explodes all the layers outwards. So sort of a little bit counterintuitively, this supernova explosion actually leaves behind a dense little core called a neutron star. And neutron stars are tiny. They're only about 20 miles across. So this is, you're not seeing the neutron star itself. That'd be way microscopic on this image, but you're seeing the hot gases right around, right there. So there's the middle star, what's left of it. And then we also just recently put out this beautiful Webb image of Cassiopeia A. And Cassiopeia A is also a famous supernova remnant in the sky. Again, I think Cassiopeia A is more like 15 light years across, expanding at millions of miles an hour. And the thing that really freaked us out about the Webb image, and there was actually a seminar today that I didn't get a chance to go to. I ended up being in a meeting. But astronomers are looking at this, and it's far more detailed. And it's almost like there are fragments that came out from this exploded stars that have somehow sort of kept together. And those fragments are full of different elements. So, we can see, for example, like which part of this is forming calcium or phosphorus or sulfur. We can see these heavier elements being formed actually in these weird little fragments that are left over from the star. Just a little aside, I'm happy to talk about it at the end if we have time, but neutron stars, we believe, are responsible for the heaviest developments. Anything that by the time you get up to gold, silver, platinum, anything heavier than that. One of the funny ones I love is bismuth and iodine. I mean, iodine is something you have in your body right now, and bismuth is Pepto-Bismol. These are things we've only seen created in the universe when two neutron stars collide. Seriously, Pepto-Bismol and iodine, something about your digestive system. It's only formed with neutron stars. Bizarre, but amazing. So I really encourage you to go to the press release about Cassiopeia A, because they go into all kinds of different sections where we're watching different elements form, different shock waves hit the gases. There's something called the big green monster that only shows up in the infrared in the very core of this explosion. Number 4 is a very strange fragmented object that at first we thought was part of this supernova remnant, but it turns out it's not. It's way farther away. It's in the background. And it's like another exploded star that did something we've never seen before. I mean, we always thought these things went off fairly symmetrically. Everything was just gas. Now we're finding weird detail in them that we just didn't know about. Yeah, there's a picture on the right-hand side of this thing we call the green monster. There's some gas structure in there that we only see in the infrared, and we're trying to figure out what it is right now and how it works. So, I mean, it's a real-time discovery. So as I mentioned, the fun thing about these things is that now more and more we're able to identify which kinds of stars produce which atoms. And as I know, I'm sure all of you know this, but I mean, in the public, I'm always just really kind of making sure they get this, that, the universe only has one way to make, say, a calcium atom that's in your teeth, or a carbon atom that makes up your body. And that's in a supernova explosion. There is not another way. The universe started with lighter elements. That's not a theory. When we look so far away that we're looking at things that are many, many billions of years old, we see less and less of the heavier elements that make us up. And as I mentioned, for some strange reason, there are some of these larger atoms, including like iodine, that we've only seen when two neutron stars collide. And we just sort of made up this new periodic table at NASA. You may want to grab this. This is all available on NASA websites, but this shows you what sort of processes make the different atoms that we know of. And you can see here, there's a few, just the Big Bang, the hydrogen, helium. There are some where cosmic rays hit atoms and cause the atoms to break apart. There's radioactive decay, dying low mass stars like the sun, white dwarf supernovae, merging neutron stars. So again, go back to iodine and all these other things that I say gold. Yeah, these are the only times we've seen these atoms made, is in merging neutron stars. And then of course there are all the things that we have only made in a lab. There are heavy elements that we put together in particle accelerators by slamming atoms together, and they stick together for like a millionth of a second, and then they break up. But hey, you can call that an element if you want. So And this was actually the image that just came out, I think it was yesterday, that I wanted to show you because this is a star forming region that's actually in one of the Magellanic Clouds. This is the Dorada star formation region. And the thing that amazes me is if you see those sort of spikes coming out of the middle, those are the classic diffraction spikes of a telescope. You get that when light starts bouncing off. Basically, it's a little too bright. You've overexposed the telescope, and the light starts bouncing off the supports of the secondary mirror. And this is a star formation region in another freaking galaxy, and we're getting so much infrared light from it that we're getting diffraction spikes. Just amazing. And beautiful structure as we sort of look at how these stars are forming. So really something. Okay, going out to slightly larger distances, of course, Webb was, some of the major scientific goals of Webb were how deep into the universe and how far back in time we could see. And so you see here, this is a beautiful Hubble Space Telescope picture, a visible light picture of a gorgeous spiral galaxy. You see all of this dark brown dust, which is the debris from the exploded stars, the heavy elements that we're made out of. So, all of the dust you see in a galaxy, that's produced by the stars when they die. And then that seeds the galaxy with all of these elements, and new stars form out of them, new planets. Add water, let it sit for 5 billion years, let it be warm, and you get us. And it's just a wonderful thing to see. That dust turns out to be incredibly connected in the infrared, where you can see the dust itself glowing. And so one of my favorite examples, this is a galaxy sort of colloquially known as the Phantom Galaxy, and it has beautifully defined dust clouds that you see on the spiral arms here. Again, this is something I kind of take for granted being an astronomer, is that I don't know if most people know that the spiral arms are not structures. They're not solid things that go around the galaxy. All 500 billion stars in the Milky Way are just on independent orbits gravitationally around the center of the galaxy. Right now, you and I are going around the center of the galaxy at about 500,000 miles an hour. And at that speed, the sun and the solar system and the Earth and everything have been in and out of spiral arms many times. So in 5 billion years, if we go around every, quarter billion years or so, we've been around more than 20 times. And we've been collecting material. This dust just comes raining down on us. And, one of the big successes for NASA this year was we actually went out to an asteroid, Bennu, and we took a pristine sample of an asteroid. So, I mean, normally we do have samples of asteroids. They're called meteorites. They fall through the atmosphere, but they can be contaminated. They've been burned, all of that. And so we went out and we actually got a sample of an asteroid that was still in space, billions of years old. And it's really a time capsule of what the cloud that we formed out of is like. 5 billion years ago, what chemistry was there? I mean, seriously, it's a sample of us. All of the amino acids, all of the nucleobases that make up our DNA, we have found in asteroid samples now. You are made directly of this sort of material. In space, all of the carbon and all of the different atoms that are made, they clump together just because of electrical forces. And you can make, especially carbon is really sticky. It sticks onto everything, it makes long chains. But it's amazing to think that in the meteorites now, I mean, not only just have we identified small organic molecules, we've identified entire nucleobases, including all of them, all of the ones that make up the alphabet of our DNA. They were already there in meteorites. So as we go around these spiral arms are denser regions, sort of almost like traffic jams as the stars go around. They're areas where things slow down and get kind of dense, but you keep going through them. In infrared, there's a very different view of the galaxy. And here's the infrared view from Webb. And now you see the underlying scaffolding. I mean, sort of the skeletal structure of the galaxy. All of these dust clouds being brought together gravitationally. As the stars move through them, they get kind of streamed out. For those of you that love, big black holes, you're right in the core, you can see that it's much more visible in infrared. The core is cleared out of dust. You don't see so much of that haze of stars. And you can see basically, these are probably clusters of giant stars, blue stars, that are orbiting, closer to a big black hole in the center. And now we're finding out from Webb that, there's a lot of star formation that goes on in the centers of galaxies near these big black holes. But you and I are careening at 500,000 miles an hour through all of this glorious schmutz that was thrown out by the stars. And you just, I love the way you see this. And as you know, this is a Hubble image of two galaxies interacting. They're going to merge into one big galaxy. And that, of course, it seems to be a wonderful part of forming spiral arms. And looking at some of these, again, this is a visible light Hubble image of the Whirlpool galaxy. And you see the dark dust, you see, all of the red areas are areas where there's active star formation along that dust. But again, in infrared, it just becomes so much more connected. So this is a picture of the Whirlpool galaxy in infrared. And as I mentioned, I mean, we all knew this, but the thing that's sort of wonderful to see in here is that as we move around and collect up all this debris from space, all of it is mixed together. You have atoms in your body from billions and perhaps even trillions of stars that have lived and died over the course of the history of the Milky Way. Somebody had posted on Facebook that there were dinosaurs on the other side of the galaxy, and I was wondering about it until I realized what they meant was that the Earth 60 million years ago was on the other side of the galaxy from where we are now. That's true. So it's wonderful to think about how we really are galaxies incarnate, that we have atoms from stars that blew up 50,000 light years away or more. On the other side of the galaxy, we've collected atoms from those stars, and they're in you right now. And so it's a beautiful view. So I think, let's see, I don't want to take up all the time. I think one of the things I'll do is I won't so much talk about the deep universe. I can if you want, but I want to add I want to end a little bit on some of the things we're finding with exoplanets, because that was another big goal of Webb, and I'll do this very briefly. When I was in college, I actually did some of the work with a man named David Latham in trying to detect the first exoplanets. And from when I was in college, where we hadn't detected them yet, to now, is just an incredible explosion, because at the moment we've confirmed over 5,000 planets that are going around, different stars in the sky, some of them visible stars you can see. But the confirmed means we've seen the planet come around 3 times. And most of these we see when we see the planet cross in front of the star and block out a little bit of the light from the star. It's called a transit. It's a tiny little eclipse. And planets are so small compared to stars that, of course, we don't actually see a little disk go in front of the star. We just notice that the star's light goes down. There's a dip because something's in front of it. And that comes back over and over again in the same pattern. And then you say you've detected a planet. So there's a real limit to that technique, because you need to wait for something to come around 3 times. And it's only been about 30 years since we've detected the first planet around another star. So something like out at the orbit of Jupiter wouldn't have had time yet. We wouldn't have been able to see that come around again. So right now, we're really only finding the planets that are closer in to their stars. And there's plenty that are around regular, big stars. And of course, if you're closer into a star, that means you're sort of a lava world. You're really, really hot. But there are also lots and lots of stars. The majority of stars in the Milky Way are much less massive and cooler than the sun. And in that case, if you have a star that comes around every couple of days or so, or every couple of weeks, even though it's very close to that star, the cool star means that it's not burning hot and just lava. And this is a star, this is an artist's conception of a planet that we've found around a star about 160 light years away. And that star, represented here by this little red glowing ball, it's what we call an M dwarf star. It's about 1/10 the mass of the sun, and actually, even less luminous, would be glowing red. But we're finding planets now that are about the right distance away to be roughly the same temperature as we find on Earth. And we don't, I mean, in the past, we didn't know much about the atmosphere, whether there was air. But one of the things that we found around this exoplanet was a lot of evidence of water vapor. And in fact, so much water vapor that this could be an ocean world. This could be a world that has oceans on the surface. And so here was sort of the promise of Webb that we're just starting to see. I mean, this is a very much, watch this space in the next couple of years. But we're actually able to take with Webb, we can separate the light that's coming from the planet versus the star, and we can make spectra of it. So we basically move it out into a rainbow. And by looking very carefully at all of the colors of light and the amount of light at each color, you can read all sorts of wonderful things, like the temperature of the gases, what the chemistry is, how fast it's rotating, all kinds of things you can read from the spectroscopy. And this is a spectrum of the planet. It's a wiggly line, but what the wiggly line means is how much light is coming out in different colors. In this case, colors of infrared, colors we can't see. And the wonderful thing is we're able to read molecules for the first time, actually find out a lot about the atmosphere of this planet. And we detected water vapor before. In this Webb detection, we're detecting methane. That's an organic molecule, carbon dioxide. It's largely postulated that if you can have oxygen, carbon dioxide, water vapor, and methane, if you can have those four things together, in and of itself, neither of those four mean that there's life there. You know, you can have plenty of carbon dioxide, like on Mars or Venus, and not have life. You can have plenty of oxygen and not have life. But if you have those four, it's hard to get them all together without there being life, without there being something putting into the atmosphere. So we're most of the way there. I think we need to get a good oxygen reading. But the thing that is really weirdly compelling and kind of gives me goosebumps about this is that this is preliminary. And this result may be spurious, which means that we make it a better spectrum, and this goes away. But there seem to be little vague detections in the light of a molecule called dimethyl sulfide. Enough so that they actually published a paper on it. So, I mean, it's not completely bonkers, but they'll definitely have to go back and make sure this is there and do a better spectrum. But dimethyl sulfide is one of the molecules we've identified as something called a biomarker. It's only made by life. And it's not that easy for life to make. So it probably means life. And specifically, dimethyl sulfide is made by plankton on an ocean world. You know, it was not my bet that the first place we would find life would be a planet in another solar system. You know, I mean, I thought we would find it on Mars, a microbe on Mars, or maybe in the moons of Jupiter and Saturn. We may still. And this, like I said, this is a preliminary result. But if this holds up, we may be looking at the first detection of life. And, you know, I think that's exciting that they may be coming up in the next few years. Now, we've seen things on Mars. Working at NASA, you know, it's frustrating because I totally agree how scientifically conservative we need to be. We will not say that something is life until we are absolutely certain. And we've seen chemistry on Mars that if we'd seen the same thing on Earth, we would have said was evidence of ancient life. Something on Mars in the soil can separate light carbon from heavy carbon. And that's one of the ways that we say that we have detections of life on Earth like 4 billion years ago. That's one of the first things that microbes do, because lighter carbon is easier to do chemical reactions with than heavy carbon. And we see that on Mars. And we see all kinds of wonderful organic molecules on the moons of Saturn, and we want to go out there. But, you know, if the dimethyl sulfide holds up, that's going to be hard to defute. So, you know, it's sort of fun to think that we might be just about there in terms of actually knowing that there's life out there. Okay, well, why don't I end there and take questions. And the questions can be about what we've talked about today, but they can also be about something else. Like I said, I mean, I have to keep roughly up on all of the science that's going on. I'm sure there's stuff that I haven't, stuff that I've missed, but if I can answer questions, I'd be happy to.
That was quite the bombshell to end on there. My gosh, we need a better name than K218b. I hope you're busy thinking of one.
I didn't even bother to put the name up there because it's just a phone number, but it's not. Yeah.
Wow, I hadn't heard about that. That's awesome. We do have a question from John Pinto there. If you want to do that one, what must have preceded the solar system that we have so much heavy elements like thorium and uranium in the Earth?
Lots and lots and lots of dead stars. So as I was saying, I mean, over the course of the life of the Milky Way, which, you know, I mean, we don't know exactly how old the Milky Way is. From what we understand of galaxies, smaller galaxies become bigger ones through mergers. And with Webb, we are seeing that. I had a little bit where we're seeing very oddly shaped sort of proto-galaxies that are kind of shaped like big long noodles, or some of them are shaped like surfboards, kind of oval, oblate things. They're coming together and merging. Right now, we're eating up several small galaxies as we speak. They're merging with the Milky Way. And of course, we're coming together with Andromeda in about 3 billion years. So when you think about all of the stars that have lived and died, and the stars that form supernova explosions don't live very long. I mean, the stars that are forming today that will someday go supernova, we think will live a couple million years before they blow up. That's not long for a star's life. In the early part of the galaxy, the early life, and this is something that's still conjecture, but I think we'll learn more with Webb. There may have been collapsing giant clouds of material that never really even formed a star. They never went stable. I mean, it could have been the equivalent of 1,000 or 1,000,000 times the mass of the sun, just coming together, forming a big nuclear fusion blast that never was contained. I like to call that the party at the beginning of the universe, and we're looking for evidence of that with Webb. Another way to talk about this is something called a population 3 star. So what were the first generation of stars like? And these stars were forming about 200 million years after the Big Bang. That's about when we think this was happening. And these are difficult things to see even with Webb, but we're hoping we're going to get lucky and see some of these things with Webb. The universe was smaller, it was denser, and I should say the visible universe. We don't know how large the actual universe is, but the visible universe that we can see now was much smaller, denser, and if dark matter turns out to be real, then much more dominated by the gravitational force of dark matter. So you could have had dark matter just forming these big gravitational cores with all the regular matter rushing onto it and forming all of these supernovas almost immediately. And so what it means that we have all this wonderful, heavy elements is that, the sun and our nebula, the cloud that we formed out of, was hugely enriched by generations of massive stars that had died before us. And like I said, the neutron star one was a relatively recent discovery. About 5 years ago, it was Hubble. We had seen most of the elements kind of up to the heavier ones being created in supernovas, but we'd never seen anything like silver, gold, platinum, bismuth, iodine, or anything like uranium. And then when we observed 2 neutrons in a binary star system merging together, and by the way, this produced gravitational waves that were actually measurable here at Earth. I love that. I mean, two neutron stars collide in a galaxy. I think the galaxy was about 150 million light years away. And the gravitational wave of space and time actually shook us enough that we were able to say, oh, look over there. And the Hubble Space Telescope went over and watched the explosion. And we saw about 10,000 times the mass of the Earth in gold produced in seconds from the spectroscopy. It's just like, oh, okay, that's where gold comes from. So, I mean, the whole idea about the neutron stars is that to make big atomic nuclei, you need a lot of protons and neutrons close together. And a typical supernova wasn't doing that. The core collapses either into a neutron star or a black hole. You get big shock waves that rip the star apart and produce all kinds of wonderful stuff. But to get the really big nuclei, you need a lot of nucleons, protons and neutrons right there sticking together. And the only thing we found that does that is a neutron star merger. So yes, we have been enriched with neutron star mergers, and not just one. I mean, probably millions of them. And not just one star, but billions, or in the lifetime, maybe trillions. I mean, your atoms don't all come from one star. They come from all over the galaxy. I love that. I think that's wonderful.
Absolutely. That's so cool. William Castro, can you talk about how much solar mass is needed for a star to become a white dwarf or a neutron star?
Yeah, sure. That would be the famous Chandrasekhar limit. Chandrasekhar was a theoretical physicist at the University of Chicago, and a person of Indian nationality. And he calculated the amount of pressure basically needed, the gravitational pressure, to form the difference between these two stars. So for a white dwarf star like the sun, a solar mass of gravity, as big as that is really just not enough to set off a supernova explosion. So we'll make heavier atoms. And like I said, we might go even up as far as carbon. But after that, there isn't enough gravity to push to make the temperature higher, and the fusion will just stop. And so white dwarf stars can be from a range of massive stars. I mean, all of these little red stars, too, will form white dwarf stars eventually. The thing that's amazing about these little red dwarf stars is that they burn their nuclear fuel very, very slowly. And so, massive stars might only live 1 million years and explode. You've got the sun that might last about 10 billion years total. And these little red guys, they might last for trillions of years. They might last longer than the universe has yet existed. So there hasn't been time in the universe yet for these things to go white dwarf, but there has been time for things like the sun. And so that's what we'll do. The nuclear fusion reactions will go out, and we'll end up being a dense little ball of largely carbon. And that will just cool off. But what happens is if you have, I got to remember the Chandrasekhar limit now. If you have, I think it's 1.3 times the mass of the sun, it's not that much different. But if you have about 1.5 times the mass of the sun, then you have enough mass to keep the nuclear fusion reactions going past carbon. And so you can fuse bigger and bigger atoms. And then you get to a real problem, and that's the element iron. So shortly, I mean, I love this. I love this whole story. But large atomic nuclei like uranium are really unstable because the force holding them together, they're physically big nuclei. And the nuclear force from one end can't really feel the other. And so what they really want to do is they want to break off into smaller nuclei to be more stable. And so for very large atoms, you get energy from fission, from breaking them apart. And from small atoms, you get energy from actually fusing them together because the nucleons now have basically overcome electromagnetic repulsion, and now they can settle down under the nuclear force and actually give off energy. And there's an atom that's right in between those two, and that's iron. Iron is right in between getting energy from fusion and energy from fission. And when you try to fuse iron, you don't get any energy out at all. And so the poor star is busy fusing atoms, it's going along happily, and then it gets to the element iron. And all of a sudden it fuses it, and that absorbs energy. And it collapses within 1/4 of a second later. Really. I mean, we believe, because I mean, you've got this whole giant star, the nuclear reactions all go out at once when you try to fuse iron in the core, and then the whole thing collapses together and goes unstable and explodes. So the thing that sets off the nuclear reaction that makes a supernova is the element iron. And you need to have enough temperature and pressure inside your star to go that high, to fuse that big of an atom. And so that I think that clocks out at about 1.3 times the mass of the sun.
Cool. Yeah, I always knew iron's where the story ended, but I never knew why.
Yeah, sorry, nuclear physics in 25 seconds. I actually lecture at CERN, in Switzerland at the Big Particle Accelerator. And we go a lot into what the nuclear force is and what it does to nucleons. But that's the very short answer. The thing that I always love to say is, protons and neutrons are not little balls, actually. They're all vibrating energy things. And so it gets far more complicated than that. But I've got a great video. I mean, I can even play it now, but it's a short video about how we observe neutron stars. I think it may be a little bit too much. Invite me back and we'll spend the whole night on neutron stars.
You're on. Absolutely. Cool. Got time for one more?
Sure.
All right. Todd Parker asks, if SpaceX figures out Starship and could at some point get out to JWST, would it be serviceable?
Yeah, it's an interesting question. I mean, I specifically, I don't know if Starship would be able to do it because Starship has more of a landing capability. And this, I mean, you might not need that. The idea is, could we build anything to get out to Webb, to L2? And I mean, of course, the answer is yes. The main thing is would that be basically, would a servicing mission be more expensive than building a new one?
Right.
It kind of comes down to that. Right now we don't have anything to send astronauts out there, and they could, conceivably fix it, put more fuel in it, put new instruments in it, whatever. There was a lot of debate at NASA about whether we should actually design Webb to be easily fixable by astronauts and hope that someday there would be, a spaceship that could take us out that far. There's a little bit that's possible, but once again, it all came down to cost cutting. In order to make things more serviceable by astronauts, they would have had to be designed in a different way. So, it's possible. I think that they would find that to send humans out that far right now wouldn't be cost effective, that you could just build another one. And the one, so we're working on a couple of big space telescopes right now. The next one we're building right now is called Roman, after Nancy Grace Roman, the first head of astrophysics at NASA. And Roman is going to be trying to go after the dark energy problem, trying to figure out how the expansion of the universe may have changed over time, which, as you know, is not something we expected. Two of my friends got the Nobel Prize for that in 2011. One was a friend of mine from college, and one was our teaching assistant, who was a graduate student. And those two men, Adam Rees and Brian Schmidt, shared the Nobel Prize with Perlmutter, Saul Perlmutter, and so we're going to try to figure out if we have evidence all the way back to the beginning of observable time of maybe the Big Bang accelerating, decelerating, going different rates. And then the one after that now that we're just sort of pooling the finances for is going to be called the Habitable Worlds Observatory. And just like it sounds, this is going after exoplanets and really hammering down which of them have life on. And so I'm really hoping, quote unquote, by the end of my life, I'm knocking wood, so it's not, too soon. I'm hoping by the end of my life, we really do have solid scientific proof that there's life elsewhere. I think we most likely will.
Wow. That'd be amazing. I hope you're right. What a time to be alive, literally.
Yeah.
Cool. Thank you so much. Yeah, I mean, I can't thank you enough for spending your time with us this evening, and it was awesome. I see lots of people clapping. You would hear thunderous applause if they weren't.
Oh, I know, but no, seriously, have me back, and you know where to find me. And if there's anything you specifically want to ask, it could even be a short question and answer thing. If there's any pressing questions from NASA, just let me know.
All right, awesome. Thank you so much, Dr. Thaller. Hope to see you again.
Bye.
Thanks. And now let me see if I can figure out PowerPoint. Let's see here. That was cool. All right, share screen. Screen 2. Share. All right. Yeah, so let's do a quick rundown of upcoming club news real quick. And our next dark sky event out at Geneva is slated for February 2nd or 3rd, weather permitting, whichever day is better. We'll go with that. Our usual crew will make the last minute call there as to whether or not we're going to go forward on that or not. Hopefully the weather will cooperate. We want to get together and do that members helping members thing again. So if you have new gear that you're trying to figure out, the Geneva events are a great place to show up and get some help from fellow members. Do make sure you show up early, though, because it's a lot easier to troubleshoot stuff when you can still see it. Stay tuned for that. Our next Zoom meeting is going to be on February 15th. That's a Thursday. I did not do it on Wednesday because that's Valentine's Day. That might be problematic for some of you. 7 p.m. on the 15th. Don't miss it. We have Kelly Wienersmith lined up. She's the author of A City on Mars. You may have heard some buzz about this book. Kind of challenges a lot of our assumptions about whether it really makes sense to send people to the moon and Mars right now. Turns out the Mars is kind of a terrible place. But if you have questions for Kelly, do send them my way and we'll work them into that. It's going to be a little bit of a different format. It's not going to be a presentation. We're just going to do an interview. So kind of like watching a podcast on that one. So don't miss that one. Should be good. Also on February 17th, we have our astrophotography workshop slated for shooting the moon. Registration is required. So go hunt in your emails for the link to that if you haven't seen it already. Do bring your own gear if you want to follow along, and make sure you have the gear that you need. If you have a DSLR or a mirrorless camera, make sure you have the appropriate T-ring and T-adapter to connect that to your telescope. I'll be sending out some more links on that shortly to our attendees. Thanks to our mentors who have signed up for helping people out there. Derek, Wes, John, and Mark will be there on hand to help you make the best out of your moon photos there. So that should be fun. Upcoming outreach events, these are the ones I know about. There's always new ones coming up. St. Cloud Elementary on the 25th. Gosh, that's tomorrow. Wicklow Elementary on the 1st. Princeton Elementary on the 2nd. Great Claremont Campout on the 3rd. And the Canaveral Seashore Star Party on February 3rd as well, out here in my neck of the woods. Lots going on that weekend on the 2nd and 3rd. That's also the same weekend as our Geneva Dark Sky event. So lots of events to choose from there if the weather cooperates. Fingers crossed. Umatilla Elementary coming up on February 7th. Cub Scouts 207 and 46 coming up as well. And we'll do the rest of those after our next online meeting. If you'd like to participate, get out there and share your telescope with some kids and some adults and get them inspired. Contact outreach@cfas.org or go ahead and just respond to the threads on cfas.groups.io that are calling for volunteers. It's a very rewarding activity, and I encourage you to do so. December's outreach, just to acknowledge some of the people that helped out in December. We had events at Busnell Elementary Powderhorn event for the Boy Scouts, Eustis Memorial Library, Pinecrest Elementary, and Telescope Thursdays events. Thanks to everyone who participated in that. And if I forgot you, I apologize. This is the list that I have. But Phil, Doug, Len, Mark, Eric, Al, John, Derek, Wes, and everybody else, thank you so much for participating in our outreach events. It does make a difference. Astronomical events coming up. So lots of fun stuff coming up in the coming month. Don't forget the eclipse is coming. I've seen a lot of chatter on Groups.io about people's travel plans. So it's almost too late, but it's not too late to get out there if you find the right spot. If you want to go out there, it's supposed to be a life-changing experience, and this is probably your best shot to see it for a very long time. There is another full total eclipse coming over our part of Florida, but that's quite a few years away. January 25th, which is tomorrow, is the full moon. And unless you're a werewolf, that's not good news. You know, that's going to wash out things, and it's not the best time to look at the moon either. But on February 9th, we have a new moon. So that will hopefully have better weather and allow us to take advantage of those dark skies. February 16th, thanks to John Starr for reminding me of this one, the lunar X and V will be visible at 6:45 p.m. So if you train your telescope right at the terminator, you'll see a feature known as the lunar X, and you can see a little preview of that here in this little image here. It's not really an X, it's just a trick of the light on a few craters, but it's kind of a challenge to observe it because you got to be looking at just the right place and just the right time to see it. So that's always a fun thing to check out. Jupiter is still looking great in the sky, so make sure you take a look at that if you're out at night with your telescope. And a couple of conjunctions. Mars and Mercury will be within 15 minutes of each other on January 27th in the morning. So if you're up early on the 27th, look up. You might see something cool. On a more somber note, our former treasurer, Kent Allingham, unfortunately passed away a few days before Christmas. And I just want to say a few words about the great job he did as our treasurer. For many, many years, he kept this club humming. And, we kind of took it for granted, quite honestly. And he just made it all work. He was a great treasurer and a great guy. We miss you, Kent, wherever you are. Kent left us one last gift, though, before he went. He actually bequeathed to CFAS his software bisque Paramount or Mighty Mount, more specifically, in pretty much brand new condition. This is an observatory grade mount, folks. In fact, it's the same mount that's in my observatory in the backyard. So this is a pretty good package here to pick up. His wishes were that we just do whatever we want to do with it and just use that for the benefit of the club. This is a little bit much of a mount for the loaner program. So what we want to do is offer this to the club. So if you're interested in purchasing this mount, we're going to be asking $6,500, or the best offer that we get. It is worth $10,000 new. So that's actually a pretty good deal if you want to get a top of the line mount here. I have one of these. I don't even need to use a guide scope with it. Like, it's that good at tracking. So it really makes life a lot easier. Proceeds of that will go towards CFAS member benefits. It goes into the CFAS treasury and lets us do more stuff for you. If you're interested, contact Christopher Hunt at loaners@cfas.org to take advantage of that deal. Also, I want to mention that before Kent passed away, we did have the opportunity to go out there and thank him for his service shortly before. John Frank and I went out to his home and presented him with a plaque thanking him for all he did. And, it was good. We had a good little goodbye there. Thank you, Kent. If you are willing to help out, the CFAS Board of Directors needs you. So we do have a well-staffed board of directors, but we need a hand. We need continuity. We need people to kind of pick things up. So if you're interested in helping out behind the scenes and making CFAS happen, please let me know. president@cfas.org. Our biggest needs right now are for the treasurer and membership roles. Right now, we got one guy, John Frank, doing both. So he could use a hand, people, if you're good with money, or if you just want to help out on keeping track of our membership and sending out renewal reminders and things like that. Please let me know. We'd love to welcome you to the board of directors. We're always looking for folks to help out with that. And with that, let's go to our Astrophotography Showcase. Let me check the chat real quick here. I think I see I got someone. Oh, directions to Geneva, David Legros. It's hard to explain. There is a link in the event. So if you go to the calendar in cfas.groups.io, I believe the event there gives you some directions. The short story is if you look for the Geneva Gun Range in Google Maps, that should bring it up. It's actually a training center for Seminole State College's law enforcement program. So they let us use it at night. It's out by not too far from where the dump is in Geneva, if you're familiar with that. But yeah, there are coordinates there in the invite that will let you find it with GPS. All right, Astrophotography Showcase. Somehow I put myself first this time. Yeah, so we had some pretty lousy weather these past couple of months, but we had a few good nights. So we got actually quite a few submissions this time. This is my little picture of the California Nebula, or a part of it. The California Nebula itself is huge in the sky, and it can't all fit in my telescope. So this is just one little piece of it. Shot over about 3 nights, I think it was, and kind of challenging to get that blue glow there. You see, that's actually ionized oxygen there, which is pretty hard to pick up out here in light polluted skies. The rest is ionized sulfur and hydrogen mostly. This is a false color narrowband image shot from my backyard. The other one I got is the Spider Nebula, and I can kind of see it. Maybe use your imagination. A little spider. Maybe that's the thread that is coming down on the top. I don't know, but not a lot of blue in this one, folks. So for my fellow astrophotographers, don't bother trying to collect oxygen on this one. Don't waste your time. It's all hydrogen, pretty much all. What's interesting, though, is that just out of the frame, there's another nebula called the Fly Nebula, which is like a much more compact little thing. So get it, the spider and the fly, kind of a neat thing. If I had a wider field of view, I could have done that. One cool thing I wanted to share, though, on Saturday, I took this picture of the sun using my Lunt 40mm solar telescope. And remember, the sun came out on Saturday. Wasn't that something? It turns out, I was just reading today, my wife sent me this article saying that a massive solar flare came off the sun on Saturday. It's like the biggest one in 7 years. It's actually a coronal mass ejection that was heading our way. I think it already hit us, so we're still here. I guess it wasn't that bad. But one of these tendrils here must have been it. I'm kind of thinking it's that big one on the center toward the top there. And with that, let me, Wes Klum, are you here? Sure, if I saw you. If you are, go ahead and take yourself off mute. Let me check the participant list real quick here. Wes is always an excellent source of astrophotography. And I don't see him here, so I'll just go ahead and share this one with you. Awesome shot here. I believe someone helped me out here. I'm not sure which object this is. Wes, if you were here, I'd let you talk about it, but Wes can maybe send us a note later on. I can see the a lot of blue ionized oxygen in that one, which is also really cool to see. He always puts in a lot of time into these images and gets some really rich colors out of them as well. So awesome stuff. Wish you were here to talk about it, Wes. Maybe next time we'll put that back on. Jeffrey Birch, are you here? Go ahead and take yourself off mute if so. No, don't see him on the list. He sent in a bunch of stuff. A lot of it's from his Sea Star, turns out, and a few nightscapes as well. So there's a nice little shot of the Milky Way from Jeffrey Birch. And another one at a little bit of a different angle there. You can see a few streaks there from, looks like he caught a meteor there, that green streak there. That's pretty cool. And also a few shots from his new Sea Star. If you haven't heard about the Sea Star, that's all the buzz lately. A little self-contained unit at a very affordable price point that can take deep sky images through live stacking and allow you to share that on your cell phone. So here is, looks like the Whirlpool Galaxy with its little friend there, M51 and M51b. Pretty impressive, for 6 minutes. Gotta say, the Sea Star is a pretty neat device. It's kind of like a little miniature observatory, and it does it all automatically. You just plunk it down, and it does its thing. So pretty interesting to see where technology is going in astrophotography. Eric Moore, I know you're here. Want to go ahead and take yourself off mute?
I am here. Thanks.
Cool. What do we got?
That is I believe, the first Sea Star image that I captured. I can't remember if this was when we were at Geneva or not, but I really love the Sea Star. It's actually out there right now capturing a few things. But this is Andromeda.
Indeed. A quick question, like how deep can you go with that Sea Star? Like how long of an exposure can you practically go?
Well, I think it depends on how, where the object is, because you'll get a lot of rotation with the Sea Star, and it'll kind of mess up your image if you go too far and if it's above 85 degrees. So I think the longest that I've done has been about 70 minutes, 71 minutes on
That ain't
one
bad.
object. Mm-hmm.
Yeah. Cool. Yeah, I see a lot of like 5-minute ones, and I've always wondered how long you can go, but you can definitely get
Oh
some
yeah,
good
much
stuff with an
longer.
hour. Yeah.
Yeah.
Cool. Cool launch
So
photo.
yes, this is I believe the ULA, no, not the ULA. Which one is this? Yeah, ULA Vulcan launch. I had the privilege of being picked to photograph the launch from the top of the VAB, which is very rare for photographers. And so I tried to do everything I possibly could do while I was up there, including a streak shot, which we normally don't do that close to the pads. But I was able to pretty much catch it. It clipped right at the apex, but just wanted to show that streak shot from ULA Vulcan.
Yep. Very important launch. Whole new rocket system and first flight of the
Yeah,
new Blue
first
Origin
flight.
engines as well, right?
Yeah.
So
Carried the Peregrine lunar lander, which unfortunately did not
yeah,
complete its mission.
indeed. But lots going on at Blue Origin out here, I gotta say. We're down the street from their factory, and
Yes, it
there's a lot
is.
of activity lately. I think they're gonna come out and surprise us soon.
Yeah, lots of stuff going on.
Cool. That's cool.
So this is, I think the Falcon Heavy USSF 52 launch. Those nighttime Falcon Heavy launches where the boosters separate and start to return to Earth and land at LZ7, LZ1 and 2, create this beautiful, what I call booster nebulosity. And the boosters are flipping and they're igniting and they cause this just beautiful display in the sky. And you can really see it, with your naked eye, but captured these during that launch.
Yeah. That was a beautiful one. I watched that as well. It's anyone who can see a Falcon Heavy with those two boosters coming back, my gosh, do it. It's one of the most beautiful things. And
then last, I think this is one of my remote cameras at the ULA launch. The ULA Pad 41 allows for us to get very close to the rocket. Oftentimes, photographers will put their cameras right in the exhaust path to catch that exhaust. And we had quite a few cameras that got damaged during this launch, but it's a lot of fun and you get these great shots with the remote cameras.
that's amazing. What an opportunity. Great shot. That's incredible. Like I can just see like all that junk coming out of those solid rocket boosters. It's
a lot of stuff on this launch. Yeah.
Wow. Crazy. Awesome stuff. Thank you so much.
Mm-hmm.
And that is the end, folks. Let me stop my share if I can find the button here. So yeah, again, do be sure to join us on February 15th for our next show. We got Kelly Wienersmith, author of A City on Mars. If you've read this one or have questions about space settlement, send them my way and I'll make sure to pass them along. About halfway through the book myself here, so I got some work to do. All right, thanks everyone, and I hope to see you at our next event. Thanks for tuning in tonight. What a great meeting. See you next time.